Okay, the first one, ozone. How do you draw a structure of ozone? It's O3, right? So that means O must be in the center, surrounded by two oxygens. Right? So I'm going to connect these three together then. So last time I mentioned that for oxygen there are a few shortcuts. So the first thing that you should try, you don't have to try a single bond because it will not work for this case. If it's a single bond, then you have to have this oxygen being connected to two single bonds. So what I try first is a double bond, right? So double bond to this oxygen is happy. It has achieved 8 electrons. Then what about this oxygen? 1, 2, 3, 4, 5, 6, right? So what can you do? Can you interact with this oxygen via a double bond again?
No.
Then you have 8 electrons, right? That's right, more than 8 electrons, right?
Yeah.
So what do you do now? You're only left with one last choice, which is to share both of these electrons with this oxygen, correct? In a dative bond. So this is the only way that you can achieve an octet structure for all three oxygens. So the final structure should be like this, alright? And then you have a lone pair here, lone pair here, lone pair here.
What is that?
The arrow is a dative bond. It was mentioned last week when you were not here. A dative bond simply means that these two electrons both are shared by this oxygen. Usually a covalent bond is made up of two atoms sharing one or two, sharing 1, 2 or 3 electrons each. But for this case, both electrons come from one atom. Alright, next one is the azide ion. So how do you draw a structure of azide? Taking inspirations from ozone. Alright, how do you think you can construct azide?
And also it's an ion.
How do you construct azide? How are you going to connect these three nitrogens? You have nitrogen 1, nitrogen 2, nitrogen 3. Alright? So basically, this structure is something like this. Alright? This question, if you don't know what to do, is okay for information. Alright? Because this is one of the harder examples. So this is actually the structure of azide. Alright? Sorry. This is actually the structure of azide. So in azide, what happens? Basically, if you look at this, let's ignore the charge first. Let's form one bond first. Alright? So let's say this central nitrogen forms one bond with the terminal nitrogens. So nitrogen is from group 5. This is how you look like. And this is how you look like. Alright, and then this central nitrogen will be left with 1, 2, 3 electrons. So at this instance, you can see that none of the atoms over here achieve the octet configuration. So what happens is that this nitrogen will share one electron with this nitrogen again. So let's say this one share with this one to form a bond. Alright? So now this nitrogen, did it achieve octet? No, right? It has only got 7 electrons. So what about this nitrogen? It has achieved octet. But what about this nitrogen? It hasn't achieved octet. So what can actually happen is that this nitrogen, alright, can actually donate this electron, alright, to this nitrogen. In a sense, it forms something like this. Alright. So at this instance, you can see that this nitrogen, and this nitrogen, for these two nitrogens, they achieved the octet, but for this nitrogen, it didn't achieve the octet. But remember, there's a negative charge over here. Alright, so what can a negative charge do? The negative charge is actually an additional electron. It can actually go to this nitrogen. And at this instance, you can see that all three nitrogens achieve the octet configuration. So this is some advanced level of chem bonding. That's why I say if you don't know how to do, it's okay. Alright, it's just for information.
Legit,
Yeah. So if you're confused with this one, alright, don't confuse yourself further. Alright, it's for information, for your enrichment. If you look up the structure of azide, you can see that there's a few structures that's possible for azide. That's actually due to the what we call a resonance effect, which is not in your syllabus. If you're interested, you can go and read upon it. Next one is ethane, C2H6. This is kind of easy, right? So we know that each carbon can connect to 4 atoms, whereas each hydrogen can connect to 1. So this is the only structure that ethane can adopt. Whereas for ethene, alright, C2H4. In order to form C2H4, you have to have a double bond somewhere, so that the carbon has got 8 electrons. Alright, whereas the ethyne, C2H2, basically you are changing the double bond to a triple bond. So you can see that from ethane to ethene to ethyne, you get 2 hydrogen less. So basically, these 2 hydrogens, they are gone, you form a double bond. That's how you get ethene. These 2 hydrogens, they are removed, and that's how you form ethyne. Yeah, and then you have propane. Propane basically is somewhat similar to ethane. Alright? Everything is CC bond or CH bond. This is propane. And then you have propene over here. So based on the name, right, you should suspect that it contains a double bond. Alright? So this is propene. And next, you see that this is called propene, this is called cyclopropene. Although they are molecular formula, they are the same. So for this case, we say that these two, they are isomers. Right? You will learn about isomers in next year during organic chemistry. So C3H6, basically what I want you to do is just to draw another possible structure. So based on the name cyclo, alright, it actually contains a cyclic ring. Something like this. Alright, so did I violate any octet rule or whatsoever? No, right? Each carbon still have 8, 8, 8. Nobody say you cannot form a ring, right? So sometimes you have to exercise a bit of creativity and think out of the box. So this is cyclopropane. And then next we have here H2O2. Have you heard about a joke about H2O2?
Yeah.
A chemist walked into a bar and ordered H2O, and then his friend said, I want H2O2, and then he died.
The one I heard is primary school.
So I told you that the molecule is symmetrical, alright? Symmetrical means there can only be 2 possibilities, right? One is HOOH, one is OHHO. Correct? Can it be OHHO? Can it be OHHO? Cannot, right? We know that hydrogen can only have 1 bond. But now, if it's in the center, it must have at least 2 bonds. So it should be the first possibility, alright? So therefore, this is the structure of H2O2. Remember to fill in the lone pairs. If you don't fill in, you'll get it wrong. So H2O2 is commonly used to clean your contact lens. Alright? And then you have here hydronium ion, H3O+. So once again, we place the atom of the least number in the center, which is O, and the 3 atoms symmetrically around it. Alright? So oxygen will interact with this hydrogen via a single bond first. Interact with this hydrogen via a single bond. That's pretty much the only way to bond a hydrogen to an oxygen. And then what happens next is that this oxygen actually has got 2 lone pairs left. Alright? So now, if let's say you have a H plus that's approaching, H plus is just an acid. Now, let me ask you, how many electrons are there around this hydrogen? 0, right? So it's not stable. What about this oxygen? It has 8, so it's stable. This hydrogen has 2, this hydrogen has 2, so it's stable. So how do you make H plus stable? And how do you interact? Basically, you have these 2 electrons, right? Both electrons can actually be shared with this hydrogen.
Yes.
Alright, via a dative bond. So by sharing it this way, this oxygen is still stable, right? Because it still have 1, 2, 3, 4, 5, 6, 7, 8. But yes, arrow means share both. Think no, arrow doesn't mean I give you. Give means ionic. Arrow means share. Doesn't have H plus. You're talking about H plus. H has 1 electron. H plus have none. It lost 1 electron. Alright? So basically, the correct structure of H2
So
or
the arrow
H.
is just like if like one of the atom is the one contributing the sharing
Yes.
only.
Correct. So basically the structure of H2O plus is this. Alright, think of the overall positive charge. Alright. So next one is Na2CO3. So sodium carbonate. You're wondering that sodium carbonate is an ionic compound, right? What does it appear here? Huh? Why do you think so? Why does sodium carbonate appear here?
Because the CO3 is a covalent bond.
Have you ever noticed the structure of Na2CO3? It actually contains 2 sodium ions, right? And then it contains 1 CO3 2 minus ion. But do you know that for the CO3 2 minus ion, it is actually covalent? Did you notice? In other words, sodium carbonate contains both ionic bonds and covalent bonds. So this is the structure of Na2CO3. So how do you get the structure? Basically the main focus is on the CO3 2 minus. How do you get the structure of CO3 2 minus? Remember what I mentioned previously? I mentioned that for oxygen, especially oxo anions, right, I mentioned here. Alright, for oxo anions, for example CO3 2 minus, NO3 minus, you have as many these type of bonds as they are negative charges. In other words, for CO3 2 minus, right, you will have definitely 2 of these kind of charges, 2 of these kind of bonds connected to this carbon. And then for the other oxygen, basically you can just settle it with a double bond. Same goes for NO3 minus. Since there's 1 minus charge, you have 1 of this, and then you just have to settle the other 2. So there's a shortcut for these 2. Alright? And then for CO3 2 minus, usually we don't allocate the negative charge to a single oxygen, but rather we put the negative charge outside. So it's 2 minus on the outside. But this 2 minus means, if you wish to indicate that one of these electrons come from elsewhere, in other words, come from sodium. Right? But usually we don't do so because it is known already. And the next one is aluminium hydroxide. So same thing, aluminium hydroxide is made up of Al 3 plus, right, and OH minus. So OH minus, same thing, it is also an oxo anion. Alright, so this is the structure of aluminium hydroxide. It also contains both ionic and covalent bond. So same thing, you can think of this as, wow, these electrons come from elsewhere, which is from aluminium. So only these 1, 2, 3, 4, 5, 6 electrons were the original electrons from oxygen. And last one is ammonium chloride. So same thing. But take note, for ammonium chloride, you have a dative bond as mentioned previously. Alright, so this is the structure of ammonium. And then you have a Cl.
I think my school doesn't cover the dative bonding.
Yeah, so previously I mentioned that for dative bond is for your information. Alright, but I mean the concept is quite easy. Some schools teach, some schools don't teach. Some schools don't teach, but the exam come out. Some schools don't teach, but the exam don't come out. So see where you want to place your bet. It's like, I don't know. Your family history don't have any, diabetes cases. So are you gonna buy insurance for diabetes next time? Don't know, right? Yeah.
Oh, correct, I got diabetes.
Yeah, correct. Then later you got diabetes, then how? You blame who?
So I blame myself.
So the last one, PCl4NO3. So previously, in the previous page, I made you draw PCl4 plus, right? So you know that PCl4 plus has got this structure. Alright, you just have to fill in the lone pairs on the Cls. And then you have NO3 minus. So how do you draw NO3 minus previously? I already mentioned. So this is the structure of NO3 minus. Alright. So take note if you want. Alright. One of these electrons come from phosphorus. This is the structure of PCl4NO3. Alright? So you can see that for most of these ionic compounds, they actually contain, although we say that they are ionic, they can actually contain covalent bonds as well. So these kind of questions are always come in the form of MCQ. Right? They give you some compounds and they ask you, for which of the compounds below it contains both ionic and covalent bond. Alright? So you really have to sometimes draw it out to see
So the bottom
whether it contains.
Or is ionic.
Yes. So these are covalent bonds, obviously. Covalent bond, covalent bond, covalent bond, covalent bond, covalent bond. And then between the ions is ionic. Alright? Take note that previously I also mentioned, even though we draw dative one like that, it is still a covalent bond. So we just treat it in a similar way as single bonds, just that they are drawn differently. Alright? Now the next part is on, we'll be focusing on how bonds actually form. Alright? So just now we have been drawing dot and cross, single line very freely. But how do atoms know how to interact to form a bond? So we'll be focusing on this part for now. So first we'll begin with the very easy one, single bond formation. Alright? So the simplest of the simplest case, hydrogen. So for hydrogen, you already know how to draw a dot and cross and the Lewis structure. So what actually happens is that we have to consider in terms of orbitals. Alright? So if you look at the diagram here, we know that each of these hydrogen has got one electron in the 1s orbital, right? This one I hope you know. You should know by now. So now what actually happens during bonding is that the 1s electron of one hydrogen and 1s electron of another hydrogen, they will approach each other in the 1s orbital. Alright? They will have opposite spins. Why do we have opposite spins? Why not the same spin? Why not both of them point in the same direction? What rule will be violated? What rule is that? You learn it in atomic structures, right? That is called Pauli's exclusion principle. No two electrons can have the same spin, or rather same quantum number. Correct? So that's why both of them must be in the opposite direction. So when you interact with both of them, what happens is that this 1s orbital, alright, will overlap, what we call head-on overlap. It's like a car collision, car crash, head-on overlap, head-on crash. And this overlap will produce what we call a sigma bond, alright? Which we'll see later on. So this is how hydrogen gas is formed. But what about other gases, for example HF? If you look at HF, now things get more complicated. You can see that F has got a bunch of lone pairs around it, on top of the single bond. So what actually happens, same thing, we are going to analyze it in the same way. We have the energy diagram over here for hydrogen orbitals. This is the 1s orbital. And for phosphorus, it has got 7 electrons, and this is how its orbitals and energy levels look like. I hope you should know how to draw. Alright? So what happens is that you can see that this electron, which is unpaired from fluorine, is in a 2p orbital. So in order for this orbital to have a electron pairing to occur, it have to overlap with this hydrogen. So once again, it undergoes a head-on overlap to form this kind of orbital interaction. And once again, this is known as a head-on overlap because it collides, or rather it overlaps with the other orbital directly in one line. So now, we mentioned that this orbital interact with this orbital, right? Then what about these 3 orbitals which we didn't talk about? If you look at the structure of HF, HF has actually got 3 lone pairs, right? So one of these will become one lone pair, and that's how you account for the lone pairs. So basically, the electron which interacted will form the bond. The electrons which we didn't touch, they will become the lone pair. Alright? So they become the lone pair. So even more complicated. We have 2 fluorines. Alright, and then you have so much more lone pairs. So how do you consider this question? So same thing, right? We can begin by constructing energy levels. So for one of the fluorines, alright, you have 7 electrons. For the other fluorine, you also have 7 electrons. Alright, so same thing, we are going to draw the orbitals. So this is one fluorine, always remember to shade one side. And this is another fluorine. And we know that for the fluorine on the left, we have one electron which is unpaired, and for the one on the right hand side, same thing, one electron which is unpaired. So now when both of them approach each other, I use another pen. Alright, they can undergo once again head-on overlap. So this head-on overlap will generate something like this. Alright. And once again, this is another kind of head-on overlap, because after all, both of them form in this way, right? So it's quite obvious why is it called a head-on overlap. So in fact, alright, all of the bonds that we have mentioned just now involve head-on overlap. That's their similarity. So there's actually a name given to these type of bonds. They're actually called sigma bonds. So therefore, as long as it's head-on overlap, we say that it's sigma bond. So therefore, sigma bonds, as a summary, they are formed when two orbitals overlap head-on. It could be between two s orbitals, as in the case of hydrogen. Alright, two p orbitals, as in case of F2, or an sp orbital. In other words, a hydrogen interact with a fluorine. So these type of bonds, they are all known as sigma bonds. And one more thing to take note is that for these kind of sigma bonds, you can see that this is the nucleus of hydrogen, this is the nucleus of hydrogen. If I were to draw a line, these two electrons is always on the line, right? Same goes for this. We draw the nucleus, alright, another nucleus, and draw a line. The electron is always along the line. The same goes for this. It's always along the line. So therefore, we say that the electron density for sigma bonds are always concentrated between the bonding nuclei, and due to its large extent of overlap, it is usually very strong. So strong or weak is relative to something, right? This strong is actually relative to what? To pi bond, which we'll talk about next. Alright, so we just KIV for now. Do you have any questions so far?
So there are bonds that are not here overlap.
Yes, which we are going to talk about now.
How do you recognize it?
Which we are going to talk about now. Alright. So the previous part, any issues?
How do you recognize it, like question? Like, what is the question asked you? How many sigma bonds are there in the question? What's the easiest way to like check?
Alright, next part, we are going to talk about pi bond. Alright, just now we learned about sigma, now it's pi. So for pi bond, we have to talk about multiple bonds now. So now if you look at oxygen, this O2, alright. Same thing, we're going to analyze it this way, how it's going to form the bond. So now things get a little bit more complicated. Alright. So for oxygen, we will just talk about these 2p orbitals and these 2p orbitals, because the 2s, for simplicity's sake, we won't include it in this diagram. So for one oxygen atom, we can see that for the 2pz, it contains 2 electrons already. For the 2py, it contains 1 electron. 2px, it contains 1 electron. The same goes for another oxygen. So if we were to draw it according to an axis, we can see that this orbital, which contains 1 electron, they can become stabilized if they overlap head-on, right? Remember, electrons, they are never stable if they exist as 1 electron. It's always paired.
Yeah.
So what can happen is that these 2 orbitals, they can overlap head-on. In other words, this and this, they can overlap head-on. Correct? But then we are left with this 2py. Do you think this 2py orbital can overlap head-on? 2py is basically this one and this one, right? So if this is head-on, this is definitely not head-on. It's like car. When car crash, head-on crash, and then you have the grazing, right, by the side. So basically, this kind of overlap still can exist, but it won't be called head-on overlap. Alright, but nevertheless, let's settle the 2px first. The 2px orbital of each oxygen, they are facing each other and can undergo a head-on overlap. Alright, in other words, they can overlap in this way if I were to remove all the other orbitals for simplicity's sake once again. But the 2py, they are not facing each other, right? Just now we have seen, and they cannot undergo a head-on overlap, but they can overlap side-on. we say. In other words, they can overlap sideways. So if you compare the side-on overlap versus the head-on overlap, what difference do you see?
The electrons at the side instead of the front.
So for the head-on overlap, right, there's only one electron region which contains both of the electrons, which is here, right? Correct. What about side-on? You can have here and here. Correct or not? This is pretty much like car crash. If car crash in front, basically only your head get damaged. But if you crash at the side, your whole stretch will be damaged, right? So it's quite logical. So what does this effect? And by the way, if they overlap at two positions, this doesn't mean, alright, these two electrons, sometimes it's here, sometimes it's here. Or one electron here, one electron here. No. This means that this electron, the shared electron, is throughout here and here. It's quite an abstract idea because now we are treating electrons as particles, right? But electrons, they actually have wave property. Have you learned that before?
Yeah.
So due to the wave nature, it can exist as both here and here. Right? So it's like present in both areas. But that's not important for us. What we are interested in is actually what's the difference between these and the sigma bond that we talked about previously. So just now we say that for oxygen, alright, the overlap produces a sigma bond and a pi bond. Alright. So actually for oxygen, this double bond, one of it is a sigma bond, which is caused by the head-on overlap, and another bond is actually caused by sideways overlap. So therefore, these two bonds, one of them is called sigma bond, one of them is called a pi bond. Alright. So pi bonds are formed when two orbitals overlap sideways, and due to the nature of overlap, it can only happen between two p orbitals. Do you think it's possible to form sideways overlap with two s orbitals?
No.
Obviously no, right? For example, if you throw two watermelons at each other, how are they going to overlap? Like, how are they going to crash sideways? There's no sideways. It can only be head-on, correct or not? To me, you can draw that. So therefore, pi bonds can only be formed between two p orbitals, right? And just now, remember, I made you draw the nucleus, that line, alright, and ask you for sigma bond, where is the electron located in? So if you do the same for this case, you realize that the electron density now is no longer between the two nuclei. It's either above or below. Correct? So therefore, the electron density for pi bonds are always above and below. Alright? That exists. And due to its smaller extent overlap, it is usually what we call weaker. Same thing, you can think of it in terms of car crash. Head-on overlap has more impact than sideways, right? Now, why we say that the extent of overlap is very small? Because for head-on overlap, there's a lot of area that you can overlap with. Alright? But for sideways overlap, even though I draw that the area is very big, that overlap is actually very, very small. Alright? Apart from this, if you compare a sigma bond versus a pi bond. Sorry, drawn it wrong. This is pi, this is sigma. Alright? Now think about how covalent bonds are formed and what's the definition of covalent bond. Covalent bond is defined as the electrostatic force of attraction between the bonding electrons and nucleus, right? In other words, this nucleus is positive, this nucleus is positive, this electron is negative, this electron is negative. So therefore, what is actually holding the covalent bond is actually the attraction between the electrons and the nucleus. Now if you think of pi bonds, alright, the nucleus is here and the electrons is here. It's quite logical to say that the electrons, they are further away from the nucleus, right? So therefore the attraction will be weaker. If it's weaker, that means it will be more easily broken compared to a sigma bond. So this is also another reason why pi bonds, they are weaker. So what does this effect have on oxygen? Basically for oxygen, if you supply it with enough energy, right, this pi bond will be able to be broken, whereas this sigma bond will be left intact. Why? Because it's not already mentioned, sigma bond is stronger than pi bond. So sometimes you will provide energy, for example, in the form of light. Alright, this oxygen or this pi bond, it can break apart to form this. Alright. In other words, this bond break apart, and the electrons which were previously shared, they are unshared. But the sigma bond will be left intact because it's strong. It's very difficult to break sigma bonds. Alright? Any questions so far? If not, we'll move on to another example. Finale, alright? Nitrogen. So you can see that for nitrogen, it contains a triple bond, whereas oxygen contains a double bond. So you wonder how triple bonds are formed then. So same thing, we'll analyze in the same way. So we'll draw the orbitals of nitrogen for both of them. And we can see that for each of the nitrogen, it has got 3 orbitals containing 1 electron each. So same thing, we're going to treat them differently. The X is going to overlap head-on with the X, right? To form a sigma bond. So that's how the first interaction is formed. Alright, which is on the next page, this sigma bond. And then we have 2 sets of orbitals which contain 1 electron each. So how are we going to deal with them? Basically, we have the 2py orbital, each of them contains 1 electron. So what happens is that they're going to overlap side on to give you a pi bond. And then, in the meantime, the Z, 2pz orbitals, alright, they can also overlap side ons to give you another pi orbital. In other words, for nitrogen-nitrogen triple bond, one of the bonds is actually a sigma bond, whereas 2 of them, they are pi bonds. So that's how the bonding is like for nitrogen. This means that these 2 pi bonds will be more easily broken than the sigma bond, because once again pi bond is weaker than sigma bond. And then remember that 2s orbital which you didn't mention just now. This 2s orbital. So what does it become? What does the 2s orbital become? We have 1 electron, 1 pair of electron on each nitrogen which we left untouched, right? So it actually becomes the lone pair, right? So everything is accounted for. Now for this case, do you think it's necessary to talk about the 1s orbitals of nitrogen?
No.
Why do we only talk about 2s, 2p? Why not 1s?
It's going to be full.
Remember, for bonding, we only talk about the valence electrons, right? Is 1s the valence electron? No, right?
No.
Valence electron is whatever in the outermost shell. In other words, n equals to 2. So in this case, we only talk about 2s and 2p. We don't talk about 1s. Alright, so that's how sigma and pi bonds are formed. So now as a summary, sigma bonds, right? They are type of head-on overlap, whereas pi bond, side-on overlap or sideway overlap. So these are examples. For sigma bond, it can be SS, SP, PP. For pi bond, it can only be between PP. Electron density for sigma concentrated between nuclei. For pi bond, above and below the bonding axis. So for overlap, alright, this is effective overlap due to larger extent of overlap. Right. This, whereas for pi bond it is less effective due to smaller extent of overlap. So therefore, I also mentioned that for strength wise, sigma bond is stronger, whereas pi bond it is weaker. So it's more easily broken than sigma bond. So far we also seen single bonds, double bonds and triple bonds. Alright. So we have seen that for single bond, it is made up of 1 sigma bond, right? And obviously 0 pi bond. You cannot have a pi bond without a sigma bond. And then next, double bond. We have seen that for double bond, it contains 1 sigma bond and 1 pi bond. Whereas for triple bond, it contains 1 sigma bond and 2 pi bond. So you can see that sigma bond, basically, it must exist. Alright. Whereas for pi bond, it depends on whether it's a double bond or a triple bond. Now, let me ask you a question. Do you think triple bond is the limit?
No.
How many sigma and pi bonds can be found in the following molecule? Alright. So just now I already mentioned, basically what you have to do is that you just have to, if you are lazy, you don't want to think about it so much, you can just rely on this table. So we know that for single bonds, it's definitely sigma bond. So these are sigma bond, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So there are 22 sigma bonds. Take note that for this pi bond, it's made out of one sigma and one pi, right? So it still contains a sigma bond.
Bond is a sigma bond.
So 22. So what do you learn from this? You learn that for multiple bonds, alright, they also contain one sigma bond. And a dative bond, I already mentioned, is just like normal covalent bond, just that we draw it differently. So you treat this as a sigma bond as well. What about pi bond? We have 1, 2, 3 over here, 4, 5, 6. So we have 6 pi bonds. Alright.
Don't you guys find it cool, or is it just is it not cool?
Maybe it's blowing at you.
Or maybe it's just because I called it cool, so I'm like dying.
Cold.
The cold cause you call it cold. Okay, sure.
They can.
So next part is on bond energy. Alright. So bond energy is the energy taken during covalent bond breaking or energy released during bond formation. So take note, when you form a bond, you release energy. When you break a bond, you take in energy, obviously. Alright, otherwise how are you going to get energy to break it? Bond energy is also related to bond length. Bond length is the distance between the two bonding nuclei. So usually bond energy and bond length, they are inversely proportional to each other. In other words, the longer the bond length, the weaker the bond energy. Alright. Generally, the stronger the covalent bond, the shorter the bond length. Alright. Why is bond energy related to bond length? Just imagine if let's say this bond is so long, do you think the attraction between the nuclei and the electron will be strong? No, right?
No.
Obviously. If it's not strong, that means you need to input very little amount of energy to break the bond. Compared to, say, when you have this scenario, right, where you have two electrons being bonded very strongly. So you need a lot of energy to break the bond. So this also means that a molecule with strong covalent bonds generally has less tendency to undergo chemical change than does one with weak bonds. Quite obvious. Because if the bond is weak, you do not really have to supply a lot of energy. Sometimes the room temperature is enough for you to do it. But say for example nitrogen. Nitrogen triple bond is actually the strongest triple bond in your syllabus, alright? It has a bond energy of 944 kJ per mole. This means that in order to break 1 mole of this NN bond, you need to input 944 kJ of energy, which is normally not achievable at room temperature and pressure.
That's for one out of the three, it's not all three.
What do you mean one of the three?
Like 944 is for one.
All three. Alright? This bond energy means it's taken during covalent bond breaking to break the bond. Breaking means break all the bonds. You don't just break one. Alright? Whereas for fluorine, you can see that it's only 158. It's only a fraction of 944. So, in fact, fluorine is the most reactive gas, right? Or rather the most reactive element. You will react with almost all the other elements. Whereas nitrogen, we say that it's an inert gas, right? Because of the strong NN triple bond. In fact, this NN triple bond is only broken in the atmosphere, right? When by lightning. Yes, lightning can provide enough energy to break this bond.
Right.
Just imagine if the lightning strike you, you die already, right? Confirm.
No.
That's how energetic,
Energy.
unless you are lucky enough.
Nanosecond before the lightning strikes, all you see of the nitrogen is getting separated, right?
Yeah, so the nitrogen can be broken by lightning. So the following are some factors that affects bond energy. The first one is bond order. So all these are quite intuitive. Alright. So nothing much to talk about. I talk about bond order first. So what is bond order? Bond order simply means how many bonds there are. Obviously, the more bonds you have, the stronger the bond is, right? So you can see that for CC single bond, CC double bond, CC triple bond, the bond energy increases from 350 to 610 to 840, and then the bond length progressively decreases as well. Right. So for the same bonding atoms, an increase in the number of shared electrons results in an increased electrostatic force of attraction between the bond pairs and the two nuclei. What this means is that if you have two nuclei, alright, for a single bond, it's something like this. Alright, for a double bond, is something like this. So obviously for double bond, the attraction is stronger, right? I don't really have to elaborate. So now, if you look at triple bond, double bond, single bond, the question is, why is the double bond strength not twice that of a single bond? In other words, why isn't this, 700? Why is it 610?
Because they are already like a certain distance apart, then you want just bring it closer by a bit. It's not double.
You're getting close to the explanation, but that's not the explanation. But closer. Previously we mentioned that for this case it's made out of a sigma bond, right? For this case it will be a sigma plus a pi.
Oh, wait, you're not the same bond.
Correct? And then for this one is sigma plus 2 pi's. So what did you mention previously about pi bond? Is it weaker or stronger than sigma bond? Weaker, right? So if it's weaker, that means the additional bond energy should be smaller than 350, correct? So if you take 610 minus 350, what do you get? You get 260, right? In other words, the pi bond actually, although it is incorrect to calculate this way, but we can roughly estimate that it will be 260. Correct? Compared to sigma bond and 350, which goes with what we mentioned just now, it is weaker. Now, what about this case? Assuming sigma bond is still 350, each pi bond will be how much?
245.
245, right?
I take pride in the metal stuff.
So which is, once again, goes with what we have mentioned just now. A pi bond is much weaker than sigma bond. That's why this is not twice of it. Alright? And this is also a reason why when you provide this CC double bond or triple bond with enough energy, it is the pi bond that gets broken first. Because it only requires 260 kilojoule of energy. Alright? So this is one factor which affects it. The same goes for example, if you compare CO single bond, CO double bond, and CO triple bond. Alright, it's the same explanation. The next factor will be atomic size. So now if you compare Cl2, Br2, and I2, you can see that the bond energy decreases from 244 to 193 to 150 to 151. So why is it so? That's because when you move down the group, alright, the orbitals gets larger, in other words the bond length increases. In other words, for chlorine, alright, this orbital is formed by a 3p orbital, 3p orbital overlap, whereas for bromine is formed by 4p, 4p overlap, whereas for iodine is formed by 5p, 5p orbital overlap. Now we already learned in atomic structure that as we go down the group, the p orbitals get larger, right? The orbitals get larger. So what this means is that for chlorine, alright, you have something like this, whereas for iodine, you have something like this, basically. So although for both of them, 2 electrons are being shared, but the attraction for iodine will be weaker because obviously it is further away from the nucleus. So this is also kind of intuitive. So therefore, or another reason, another way you can explain is that the larger orbitals are more diffused. Alright? So the overlap is less effective. So this is another way that we can explain. Have you learned this in school?
No. No, we have not.
Another way? Okay. Then the last factor is actually bond polarity. So only these 3 factors, take note. So previously we have learned about polar bonds. Let's just look at the diagram on the right hand side. So if let's say you have a non-polar covalent bond, X and Y they only interact via a covalent manner. But if let's say Y is more electronegative or more significantly electronegative than X, previously we had learned that Y will adopt a partial minus charge, X will adopt a partial positive charge. Alright? So when you have a partial positive and partial negative, you have opposite charges, right? These opposite charges, they can undergo attraction. So on top of this covalent bond, you actually have this kind of weak attraction. So therefore, compared to the case on top, you expect a polar covalent bond to be stronger, right? So this is exactly the reason why polar bonds, they are usually stronger than non-polar bonds. So if you look at these 3 bonds, NH, OH versus FH. Alright, FH has the strongest bond energy. Why? Why is that so? Now if you compare NH versus OH. Previously, I asked you to practice on electronegativity difference, right? Now it comes useful. So if you compare O and N, which one is more electronegative? O, right? If O is more electronegative, previously I mentioned that you just draw a bigger delta plus, a bigger delta minus, right? Whereas for nitrogen, it's less electronegative, so you draw a smaller one. So therefore, on top of the covalent bond OH, you have very strong electrostatic force of attraction between this huge delta plus and huge delta minus. Whereas for this NH, since the delta plus and delta minus is smaller, the attraction will be weaker, right? So this,
minus is the one like gaining, right?
yeah, the more electronegative one. So therefore, an OH bond will be stronger than NH bond because OH bond we say that it is more polar. Alright, the same goes for FH. For F is even more, FH bond is even more polar because fluorine is even more electronegative. So that's why the trend is like this. Alright, the same goes for double bonds or triple bonds. For example, CC triple bond, CN triple bond, CO triple bond. The trend is similar for the same reason. It gets more and more polar. So how do we explain this? We say that polar bonds give rise to partial charges on the two bonding nuclei. In addition to the existing covalent bond, there is, alright, electrostatic force of attraction between the oppositely charged partial charges. Sorry, it should be oppositely charged partial charges. So therefore, the bond strength is greater. Any questions for this part?
Could you repeat yourself again, the more polar thing?
So if it's more polar, right, the delta plus and the delta minus will be greater, correct, than one which is less electronegative. For example, O's electronegativity is 3.5, nitrogen is 3.0, hydrogen is 2.2 for both of them, correct? Now, if nitrogen is less electronegative than oxygen, what this means is that the two shared electrons will be further away from nitrogen, whereas for this case, it will be closer towards oxygen. In other words, O has a greater propensity to gain a minus charge than N. So therefore, the charge for N is smaller, the charge for O is bigger. So therefore, if the charge is smaller, that means the electrostatic attraction between this minus and the positive, which is generated on the other side, will be weaker as well, compared to this case whereby it is stronger.
So the further away from the center.
Yeah. If it's closer towards this atom, you'll gain a greater minus charge. Like what we mentioned in ionic bonding, right? If both of the electrons go to one atom, you'll form an ionic bond, whereby you'll gain a full negative charge. So this is something like in between. So therefore, we write delta minus.
So you can increase bond energy
Mainly because of this. This is stronger than this, correct? So if you add this attraction to the covalent bond, it is actually stronger than the first one, whereby you add this to a covalent bond. So these are three factors, alright? Bond order, orbital size, bond polarity. Alright, if you have not learned about this, then in school, then I guess it's okay. Alright. So next part, I will just briefly touch on some exceptions to the octet rule. Have you learned some of these exceptions?
Yeah.
Learn, right? Yes. So therefore, it's quite hard to teach chem bonding because some schools they teach this, some schools they don't teach. Alright. And some schools say that it's for enrichment, some schools say it's compulsory. But nevertheless, I'll be talking about this part briefly and not so much. Alright. So there are actually exceptions to the octet rule, some exceptions. The first exception is what we call electron deficient molecules. So based on the name, we know that they are in need of electrons. So some molecules, they contain less than 8 valence electrons, and this is especially prominent for molecules consisting of group 2 and 3 elements. For example, beryllium, boron, etc. So based on the name, electron deficient molecules, they are rather unstable and they prefer to form adducts. Not the duck, it's the ducks. Right? We will see how they form a ducts later on. So one example will be beryllium. So for beryllium, it is from group 2. Alright? You actually form this molecule with hydrogen, BeH2. Obviously for this case, how many electrons are there around beryllium? How many electrons are there around beryllium? Huh?
2.
How many electrons around beryllium?
4.
4, right? So is it stable?
No.
Alright. The same goes for boron. For boron, it's from group 3. It can form 3 single bonds with hydrogen in this manner. So how many electrons are around boron? 6, right? So how does it become stable? Basically, if let's say you add ammonia into these two, alright? Previously we learned about dative bonds. That's why I teach you about dative bonds. If you were to draw ammonia, alright, we know that ammonia has a lone pair. Correct? So nitrogen is happy, but beryllium is not happy. If both of these electrons is being shared with beryllium, now nitrogen is still happy, right? But now beryllium gained 2 electrons. So it's closer towards 8 electrons. What can happen is that you can actually have another ammonia, alright, sharing these electrons with beryllium. So in a sense, this nitrogen will be happy, still happy, this nitrogen is still happy, but now beryllium is also happy.
Yeah.
So that's how you actually stabilize electron division molecules, by forming what we call adducts. All these are known as adducts, or rather connections with NH3. Not only NH3, you can interact with basically any molecule containing a lone pair. Now what about BH3? You expect BH3 to behave in a similar way. So we draw BH3 first, and then we draw ammonia at the side. So what do you think, or how do you think these two can be stabilized? This nitrogen can donate, or sorry, not donate, share both of the electrons with boron, right? So in this way, both boron and nitrogen will be stable, because both of them achieves 8 electrons. My voice very therapeutic, right?
No. My class, the Chinese teacher.
I tell you what, at night you cannot sleep, I just play my video and then you will fall into a deep slumber.
No, don't need. My class Chinese teacher even better. She starts talking, half the class was asleep already.
Alright. So, do you have any questions for this?
Not really.
Actually, there's a whole lot about this part, but I cut it, alright?
Because it's not going to be in our syllabus, right?
I don't know, alright? Depends on the teacher's mood, alright? Depends on the teacher's mood. So we will talk about electron division molecules. Now we talk about expansion of octet. So this is like the reverse of electron division molecules. So some molecules, they contain atoms with more than 8 valence electrons. Just now we talked about less than 8, now we have more than 8. And these can be observed for elements in period 3 or higher. Usually from silicon onwards. So this means that usually silicon, phosphorus, sulfur, chlorine, xenon, they can have more than 8 electrons. Alright, just now we say that they can have less. So why is it so? That's because for these elements, if you were to draw the orbital, alright, draw the energy levels. For example, this is for phosphorus. Alright, this is for phosphorus. If you were to draw the orbitals and the energy levels, we can see that for phosphorus, apart from 3p, there are actually some 3d and 4s orbitals, right? There's low lying. Low lying means that it's very close to 3p. Alright? Why are they low lying? Have you learned this in atomic structures?
Because there's something about the electrons, the orbitals are stacked. So the 3s, 4s and 3d overlap.
You see, you have seen this, right? Whereas this is n equals to 1, n equals to 2, n equals to 3, n equals to 4. So they get progressively closer and closer. And within each of these, within each of these shells, you have SPDF, which is also in this way. Yeah, correct. Within each of these, in other words, n equals to 2, n equals to 3, n equals to 4, within each of these, you also have these orbitals which are like this. So if you were to consider both of these effects, you actually have 3D, 3P, and 4S being very close together. So that's why I draw it this way. So there's nothing new. It's what you have learned in atomic structures. So anyways, this is phosphorus, but why do I want to highlight that they're low lying? That's because they can actually make use of these two orbitals for bonding as well, since they're very close. So let's talk about the first case first, alright, whereby it obeys the octet rule, PCl3. So for PCl3, we won't go and analyze the orbital interaction one by one because it takes too much trouble. What we'll do is that we'll just draw it on top of here. So these black arrows, they are electrons from phosphorus, which comes from it previously. And then these are the electrons from chlorine. So if I draw it this way, it simply means that one of the chlorine will overlap with each of these orbitals. So these will form PCl5. It has got 8 electrons around phosphorus, so nothing new. Alright, so this one is testable, alright, because it's nothing new. Whereas these 3s will become the lone pair. But what about PCl5? It can actually form PCl5, but if you look at this structure on the left hand side, there are only 3 electrons which can interact with other atoms, right? Basically, if let's say you have this kind of scenario, you cannot overlap because you already have 2 electrons, it's stable. So what happens is that these 2 electrons can actually be excited. So once it's excited to a 3D orbital, you have 5 orbitals containing 1 electron each. So what can happen now is that chlorine, alright, 5 chlorine, each of them will interact with one of these electrons in each of these orbital to form this kind of structure, PCl5. So this is actually how you account for the structure of PCl5. Any problems?
No.
Okay, I hope. Huh?
Is this the same as what you did just now?
Yes, correct. It's the same.
But isn't it 7 instead of 8?
Or 7? Oh, this one I haven't yet. The first one. This is what I'm going to talk about next. Right? I'm doing from the 2 first. Alright? The bottom 2. So this is how you form PCl5. So around this phosphorus, how many electrons do we have? 10, right? 5 bonds times 2 give you 10. So the next one, the last exception, is known as odd electron species or radicals. Right? So some molecules have odd number of electrons. In other words, there's no way for you to pair them up. And it is impossible to pair all of them up. So one electron must be unpaired. And the electron will be known as a lone electron, not lone pair. Lone pair means you have 2 electrons, this is lone electron. And the resultant molecule is known as a radical. So if I radicalize you, you become crazy, right? You'll fight and react with everybody. The same goes for electron species. If I radicalize it, it's going to be very, very reactive. Because remember, electrons always like to come in pairs as an even number, but this is odd. So there are some selected examples. One of them is NO. Alright? So for NO, I guarantee you, no matter how you draw, you're going to end up with 1 electron that's unpaired.
Of course.
Why?
5 what?
That's because nitrogen, how many electrons, valence electrons does it have? 5, right? Oxygen has 6. 5 plus 6 is an odd number. There's no way for it to pair up. This is just math, right?
Me.
So how do you draw the structure of NO?
Have 1 radical.
Basically, NO, alright, adopts this structure, right, whereby you have an unpaired electron on this nitrogen. There's no way for it to pair it. So this is the structure of NO. And the same goes for NO2. So N, odd number, right? O, even number. 2 times an even number give you an even number. Even number plus an odd number give you an odd number, which means you cannot pair it up. That means it's a radical. This is a quick way for you to check, by the way. If it comes out as an MCQ, which of the following is a radical, please use this method. Don't go and draw all of them. You're going to waste a lot of time. Alright, so how do you draw a structure of NO? Basically,
As long as 1 odd, 1 even, then it's definitely right.
as long as the total number of valence electrons is an odd number, it must be.
There's at least going to be 1 radical.
It must be a radical. You can only have 1 radical. Alright. So in this case, this is the structure of NO2. You can see that once again, this central nitrogen, how many electrons does it have around it? 7, right? This nitrogen is 5. Sorry, not 5. 7. Around this nitrogen also have 7. Then what about ClO2? So Cl is in the center, oxygen, oxygen. So oxygen, we know that it contains double bond, double bond. So this chlorine, alright, is from group 7. 7 minus 4 will give you 3. In other words, it has got 3 electrons, which is untouched, basically. So how many electrons are there around the chlorine?
7.
Huh? How many electrons are around chlorine?
7.
Why 7?
No, not 7.
By the way, around means how many electrons does it contain in the valence shell after bonding?
11.
11, right? We have 8 being shared, 9, 10, 11. So how come chlorine can have 11 electrons?
It's
You mentioned just now, right?
it's after silicon.
It's after silicon. Look at this over here. We say that those period 3 and above, they can have more than 8, right? See, chlorine can also have more than 8. So it's nothing surprising. So in radicals, the general rule of thumb is that usually the more electronegative atom will gain an octet of electrons, while the less electronegative gains the odd number of electrons. In other words, if let's say you have NO2, why do we draw NO2 like this and not like this? In other words, for this case, you can see that nitrogen donates share both of the electrons with this oxygen. Whereas for another structure, which some students might draw, they draw it this way. Alright, in other words, this nitrogen, alright, gains the octet configuration, but this radical is on this oxygen. So why is it wrong? Remember what we talked about in the first place about electronegativity. The more electronegative you are, the more likely it is for you to gain that electron, right? So in other words, if you compete, if nitrogen and oxygen are competing for that extra electron, oxygen will win because oxygen is more electronegative. It likes to have that additional electron. So therefore, this should be the correct one.
Wait, can't for the ClO2 can't like the Cl form they give bonds with both the O2s?
It can also form, but then the general rule of thumb is that if you can have more electrons, you tend to have more electrons. If you do that, you will have probably lower than 11 electrons.
Yeah, 5.
Alright? So therefore I mentioned, due to the unpaired electron, radicals are very reactive. They react with other radicals, so pairing of the lone pair occurs. And when two of the same radical pairs together, they form what we call a dimer. So what do I mean by this? Basically, if we talk about NO, this is the structure of NO, right? Okay, so this nitrogen has got 7 electrons. Now if you have another NO, what do you think can happen? It has got 7 electrons as well, right? So 2 odd number give you an even number, right? Odd number plus odd number give you an even number. So what can happen is that these two can interact to form a bond. Alright? So if you interact together to form a bond, how many electrons will there be around this nitrogen? It will be 8 now, right? 1, 2, 3, 4, 5, 6, 8. So therefore, this dimerization is very favorable. In other words, the radicals, yes, correct. So it become N double bond O, N single bond, N double bond O. So that's how they dimerize.
So that's 2 7.
8 what? You have to count this, remember? So it's 8, right?
And then the bottom one also have 8.
So 1, 2, 3, 4, 5, 6, 7, 8. And the bottom one also have 8, right?
1, 2, 3, 4, 5, 6.
Compared to previously they only have 7.
Yes, it's more new.
And the same goes for this NO2. For this NO2, alright, just now we draw it this way. It has got 1 unpaired electron.
Another one.
So you have another one. Both of them have 7 electrons. If they were to form a bond, then this nitrogen will have 8 electrons, right? This nitrogen will also have 8 electrons. Same goes for that ClO2. Alright, so for the ClO2,
When they will form 12.
same thing, it has got 1 unpaired electrons. So if you have 2 of them, alright, they can form a single bond, and both of them will have an even number of electrons. Any questions so far?
Not really. I hope.
No questions?
Nah.
Okay. Okay, so this is just a brief intro on the exceptions. The next part will be something more relevant, right? Is the naming of covalent compounds. How do you name them? So of course you have learned about trivial names like ammonia, water, etc. No problem. All these are some trivial names given.
Laughing gas.
You also have laughing gas, N2O.
Why is the laughing gas? It's big laugh.
It probably attack your nerves or something. Earthquake. Okay, next one. Simple covalent compounds, they are generally named by using prefixes to indicate the number of atoms on each element, and also the ending of the last element is usually changed to IDE. Alright? That's why you have carbon dioxide, carbon monoxide, sodium chloride. Alright? Most of them they are IDE. So here are the prefixes. One is called mono, in other words, carbon monoxide, carbon dioxide,
trioxide,
tri, tetra, 5 will be called penta.
hexa,
Penta, and then you have hexa.
hepta.
This is like your polygon, right?
Yeah.
Pentagon, hexagon, and then you have hepta,
Yeah.
heptagon. 8 will be octa, right?
Deca.
So generally the formula is written such that the elements are in the same left to right order as they are on the periodic table. Alright? Except that hydrogen is squeezed between nitrogen and oxygen. What this means is that if let's say I give you a structure, alright? A structure containing carbon, hydrogen, oxygen, let's say nitrogen. Alright? How are you going to write the formula, molecular formula? You can't put H in front, basically. You cannot say it is H7, H8, O, N, C3. This will be wrong because it looks weird. So the general rule of thumb is that you follow that of your periodic table. So going from left to right, carbon comes first, right? So you write C3, followed by nitrogen, followed by hydrogen, followed by oxygen. Alright, this is the general rule of thumb on how to write.
Is it up to down?
Yeah, top to down. But usually you won't deal so much of elements
Top to
below.
down.
It's most of the time is those the first and second period. Alright. So that's why for N2O3 you write it as N2O3, not O3 N2, right? Etc. And SF6, basically same thing. Alright. If you look at SF6, S comes before fluorine. Alright. So therefore it's SF6 and not F6, S, etc.
What is the
Yeah, that's why it's H2O, not OH2, for the same reason. Alright, so how are you going to name the compounds? For the first one, can you just name it nitrogen oxide?
No.
No, right? Why? Because it will clash with the one below. In other words, there's a lot of nitrogen containing compounds containing oxygen, so you have to be specific.
Dinitrogen.
So in this case, you will call it dinitrogen trioxide. Alright, to indicate how many there are. So therefore, it gives you a hint that for the one below, you'll be called dinitrogen monoxide.
Dinitrogen.
How about SF6? It'll be called sulfur hexafluoride. Alright? Because it contains 6 fluorine. You cannot just say S, sulfur fluoride. Why? Because sulfur and fluorine also forms SF4. So if you say sulfur fluoride, then are you referring to this one or this one? So in order not to make it vague, you have to specify the number of fluorines. CO very easy, carbon monoxide. Why do you have to write mono?
Because got carbon dioxide.
Yes, because of carbon dioxide. If you only write carbon oxide, then which one are you referring to?
Which carbon dioxide?
How about this?
Hydrogen iodide.
Hydrogen iodide, right? So in this case, why do you not call it, mono hydrogen mono iodide or hydrogen mono iodide? Why do you just call it hydrogen iodide?
Because it's the only one that can form.
Yes, because you cannot have hydrogen bonding to 2, right? So obviously, you don't have to put mono.
And also iodide is.
It's like saying I met this dude with 2 arms. You have to include 2 arms, no, right?
No.
Obviously, you can only have 2 arms.
Unless you can.
Unless you're handicapped, then you say 1 arm.
Or unless a person has mutated and has 3 arms.
How about this N2O4? This will be
dinitrogen tetroxide.
Take note, tetroxide. this is something related to English. When you have A and O together, you remove the A. In other words, you don't say it is tetraoxide. Alright? You remove the A, so it becomes tetroxide. This is English, this is not chem. Alright? The next one, P4O6.
Tetraphosphorus hexoxide.
We call tetraphosphorus hexoxide. Same thing. Oops.
How do you write IC?
Hexoxide. Same thing, hexa, we change to hexo because A and O, we remove the A. And then the last one will be
Tetraphosphorus decoside.
tetraphosphorus decoside. Alright, this is just for your enrichment. For 10 is called deca something. Alright. So this is how you name covalent compounds. Yeah. Because I haven't reached here yet. Don't kanchong, don't kanchong. I'm slowly leading to that point. Yeah, don't kanchong. Which is this part I'm going to talk about. Don't worry, my notes confirm have. Alright. My notes will either cover your syllabus or cover everything in your syllabus plus extra stuff. You will never cover less than your syllabus.
My school one is like jump here, jump there, then after that I like cannot match what is.
Yeah, that's why it's very hard for me to design this set of notes because I have to make sure that the flow is very well. You have to understand the basic one before you move on to the important ones. Alright? So now we'll talk about the VSEPR theory. Basically, at the start, what we talk about is bonding, correct? So I make sure that you know how to draw the bond already, then we can talk about the structure. Because if you don't know how to draw the bond, then there's no point moving to structure because you will already be stuck at the first step.
Yeah.
And then after that, we learn about bond polarity, right? So why do we learn about bond polarity? That's because after you learn about the shape, together with the bond polarity concept, then you can predict whether the molecule itself is polar. Previously, we learned about the bond is polar, whatever. So after this, we'll learn about how we determine if the molecule is polar. And after we determine whether the molecule is polar or not, then we can talk about intermolecular forces. So it's all stepwise. So it's actually very difficult to plan this chapter. So we'll briefly talk about the structure of simple molecules. This part is the most difficult part of chem bonding. Right? This is even more difficult if you are in some special programs because you have to learn a lot of shapes. For your very lucky, you all only need to know these shapes, these four. The grey out ones, you don't have to know. Correct? You correct me if I'm wrong. You don't have to learn all the shapes. You only have to learn this selected few. Alright?
No, my school be like casually includes the diagram, but like doesn't talk about it. Then everybody will be wondering, oh, so are we tested on that?
See how much insurance you want to buy? Can you either buy $1 insurance?
No, my school like really like simple stuff. Then they include those diagrams by the side.
Okay, then trust me.
Pass away.
Okay, let's go with the VSEPR theory. So VSEPR theory stands for valence shell electron pair repulsion theory. Alright? So previously we learned about ionic and metallic bonds, right? For ionic bonds, we learned that, for example, like NaCl, you adopt this kind of structure, correct? So that's quite boring because most of them that you have seen is like in a cube. Alright, so there's nothing interesting about it. And ionic bonds, what we call, they are non-directional. What do I mean non-directional? In other words, if let's say you have the ion here, there can be attraction, right? If another ion here, there can also be attraction. If you have another ion here, although it's a bit far, there will still be attraction, although it's very weak. So this is what we mean by non-directional.
Is it omnidirectional?
Whichever direction doesn't matter, there will still be interaction. The same goes for metallic bond. So for metallic bond, it is between, the attraction is between the positive cation and the electrons, right? So same thing, electrons can be anywhere, there will still be some sort of attraction. But what about covalent bonds? For covalent bonds, if I atom A, atom B, there can only be attraction, alright, within, or in other words, between these two atoms along the bonding axis. Alright, in other words, I don't see this kind of interaction in some other place. So this is what we call directional. Alright, So if it's directional, that means you have a direction. If it has a direction, that means it must have a shape. So in fact, this VSEPR theory is a theory which basically it has never failed. If you apply this theory and if you understand this theory fully, I guarantee you that you wouldn't have any problem with this chapter or with this section. So the VSEPR theory says that electron pairs in the molecule, electron pairs meaning both the bond pairs and lone pairs, they will repel each other and so move as far apart as possible to minimize repulsion. So the driving force is actually to minimize repulsion. Now what do I mean by this? If let's say you have a molecule with this kind of structure, XY2. Alright? So for this XY2, the only correct way to draw it, the actual shape is actually like this. It will be incorrect for you to draw it in a bent form, this form, or this form. Why? That's because if you draw in this form, these two will experience repulsion, right? More repulsion compared to this form. Of course, like that, you will still experience repulsion. For this form, the repulsion is even greater. So the structure with the least repulsion will be both of them vertically opposite each other. This is like saying, if let's say an explosion, I put an explosive inside a barrel, and if I tell that barrel break into two pieces, do you think both pieces will fly towards you? No, right? Both of the pieces, they must fly vertically opposite each other by the conservation of momentum also.
Why is that so easy to come out? I thought this was scary.
Correct. In other words, if you break into three pieces, it's not likely that the three pieces all fly towards you, right? There must be something for it to push in the opposite direction so that it can fly in the correct direction. In other words, these three will most likely fly in 120 degrees apart. Alright? So the same goes for our second one. For our second case, I can see that if there are three atoms connected to X, the most stable or the least amount of repulsion conformation will be like this, whereby the angle is 120 degrees. So this, and this, they are all unstable. In other words, they experience more repulsion than this. Now what if I have 4? If let's say I have 4, the most, this is what students draw. They say that the 4 right, will be bonded in this direction, but it's wrong. Remember, you can make use of the 3-dimensional space. Right? For this case, each of the atoms here, they are 90 degrees apart, correct? But if you make use of a 3-dimensional space, you can actually have an angle of 107.5 degrees. This is obviously greater than this, right? Which means they will repel each other less. So the same goes for this, you'll experience a lot of repulsion. The same goes for this, you'll experience a lot of repulsion. You experience more repulsion, right? Remember, for this is a 2-dimensional way, correct? For 2-dimensional way, the maximum that you can get is 90 degrees apart from each other. But if you make use of 3-dimensional way, because bonds that we have to make use of space, atoms and molecules themselves, they are not 2-dimensional, right? They're 3-dimensional. That's why you can see things around us. So therefore, you have to make use of a 3-dimensional space. So how do you actually obtain this? Basically, just imagine you have a cube. Alright? Just imagine you have a cube and X in the center of the cube. Alright? Now you circle these two edges and these two edges. And then you join them together to the central X. This is how it looks like, the structure. In other words, this angle is actually this angle. You have learned about Pythagoras theorem, right? All those, you can actually go and prove this easily. It is 107.5. Exactly, it should be 107.47. So if you make use of the 3-dimensional space, it's going to experience the least repulsion compared to this case. This case is 90, this case is 107.5.
So this one is like a 3-sided pyramid.
This is called a tetrahedron.
Okay. So the bottom 4 atoms are like in a 3-sided pyramid shape.
Yes, in other words, this YYY is actually these three, if you think about it. And this one is the one on top. You can, because for 3-dimensional you can change it, right, rotate it, etc. So just imagine these 3 black dots, they are the 3 Ys over here. Alright, so this is the, if you don't believe, you can go and anyhow arrange, you will see that you will never be able to exceed 107.5 degrees for each of them.
So what does
So what does this represent? Alright, if you look at the things below, alright, solid line means the bond in plane of paper. In other words, because it's very difficult for us to draw a 3D image on a 2D paper, so what we do is that we make use of limitation and then we use notations like this to denote. So this one simply means, right? Just imagine this is a piece of paper. these three atoms are on the paper itself. This one will be pointing out of the paper. This one will be pointing into the paper. This is what it means. Understand?
How does one point
The
into
solid
Maybe I shouldn't draw
wall-
it. Maybe I shouldn't draw it this way. Maybe I
The
draw it
solid
this way.
wall will be outwards.
I draw it this way.
Ah.
Understand? Easier, right? I just
So
shade it.
basically the dotted line is
Just imagine I have a
behind
shaded
the-
paper and then it cuts this angle.
So
Exactly.
basically, let's say this is the center.
Mm.
One Y over here, one Y over here, and then one of it over here, and one of it over
Yeah,
here.
correct. Basically.
The solid wall will be primary.
Yes, correct. So this is what it means. Like. That's why, due to a limitation of us not being able to draw 3D on 2D, therefore we use the wedge bond and the hash bond to represent it. So the wedge bond means it's pointing out towards the paper.
我想要
The,
发小
the hash bond means you will be pointing away from you. Alright?
我想发水位。
Can
Yeah.
So this will be a most stable form. Now the same goes if let's say you have a lone pair. I will finish this part. If you have a lone pair, this lone pair will try to stay as far away from this Y as possible. So this is pretty much like the first case. Just that you are changing Y to a lone pair, but it's still an electron. So therefore, these will be more stable compared to this, and this, because these three will experience more repulsion once again. Same thing, if you compare this to this, you are basically changing the Y to a lone pair. So once again, this will be a more stable because you experience the least repulsion compared to this. The same goes for this, alright? If you change one of the Y to a lone pair, this will still be a more stable form because the rest will experience more repulsion. So once again, the concept of this is based on repulsion, the minimization. Alright? So we'll continue on next lesson. Alright?